What if what we see is merely a shimmering veil of reality? What if the most fundamental force shaping every galaxy, every star, every thread of the cosmic web is utterly invisible? We gaze into the boundless night, seeing billions of lights, but science tells us we are blind. The vast majority of the universe is hidden from our eyes, our instruments, from our very comprehension. In the 1930s, an astronomer observed the impossible. Gravity was not working as it should. Galaxies, like phantom ships, glided through space, defying all known laws. This was not just an anomaly, it was a crack in our understanding of the cosmos. A crack that has since widened, revealing an abyss of the unknown. What if everything we know about the universe is incomplete? What if we have missed 85% of its mass? Today, we journey through evidence that challenges everything we believe to be true. Prepare yourselves. We begin. In a world where Newtonian physics reigned for centuries and Einstein's theory of relativity profoundly reshaped our understanding of space and time, it seemed we had almost deciphered the cosmic mechanism. Then, in 1933, a Swiss astronomer working at Caltech, Fritz Zwicky, made a puzzling observation while studying the Coma cluster of galaxies. Zwicky, known for his eccentric brilliance and sharp intellect, was attempting to determine the cluster's mass using two independent methods. First, he estimated the cluster's mass based on the light emitted by its galaxies, assuming a standard mass-to-light ratio for visible matter. Second, and crucially, he calculated the cluster's mass based on the velocities of the galaxies within it, using the viral theorem. This theorem allowed him to infer the total gravitational pull required to keep these rapidly moving galaxies from escaping the cluster's confines. The discrepancies Zwicky found was staggering. The gravitational mass, calculated from the galaxy velocities, was approximately 400 times greater than the luminous mass, derived from the visible light. He famously noted that the average density of the Coma cluster is much too small to represent the average density of the universe. If this is true, then the Coma cluster contains an enormous amount of dark matter. He coined the term dunkle materia, or dark matter, to describe this unseen component. His findings suggested that the vast majority of the cluster's mass was hidden, exerting gravitational influence without emitting or reflecting light. This was the first audacious hint of a profound cosmic mystery. Initially, Zwicky's audacious claim was largely dismissed by the scientific community. It was too radical, too challenging to the prevailing understanding of the universe. The concept of such a vast amount of invisible matter seemed outlandish. For decades, the anomaly remained a footnote, a curious puzzle for a handful of dedicated researchers. Scientists clung to the idea that the missing mass could simply be ordinary, non-luminous matter, faint, low-mass stars, clouds of gas or dust, which were simply too dim to detect with the technology of the era. They hypothesized that intergalactic gas within clusters could account for the extra mass, or that Zwicky's measurements were flawed. But the evidence, however rudimentary then, forced us to confront an uncomfortable possibility. If Zwicky was right, then our universe was far stranger than we ever imagined. His work laid the conceptual groundwork for a paradigm shift that would fully emerge decades later, a testament to his foresight in a time when such ideas were deemed speculative at best. Initially, Zwicky's audacious claim was largely dismissed by the scientific community. It was too radical, too challenging to the prevailing understanding of the universe. The concept of such a vast amount of invisible matter seemed outlandish. For decades, the anomaly remained a footnote, a curious puzzle for a handful of dedicated researchers. Scientists clung to the idea that the missing mass could simply be ordinary, non-luminous matter, faint, low-mass stars, clouds of gas or dust, which were simply too dim to detect with the technology of the era. They hypothesized that intergalactic gas within clusters could account for the extra mass, or that Zwicky's measurements were flawed. But the evidence, however rudimentary then, forced us to confront an uncomfortable possibility. If Zwicky was right, then our universe was far stranger than we ever imagined. His work laid the conceptual groundwork for a paradigm shift that would fully emerge decades later, a testament to his foresight in a time when such ideas were deemed speculative at best.
The true awakening to the reality of dark matter began in the 1970s, propelled by the meticulous work of American astronomer Vera Rubin and her colleague Kent Ford at the Carnegie Institution of Washington. They embarked on detailed spectroscopic studies of galactic rotation curves. For decades, astronomers had assumed that the distribution of mass in spiral galaxies mirrored the distribution of their light. According to classical Newtonian physics, stars and gas clouds orbiting a galaxy's center should slow down as their distance from the center increases, much like planets further from the Sun orbit slower due to less gravitational pull. Rubin and Ford, using sensitive spectrographs, measured the velocities of stars and gas at varying distances from the centers of numerous spiral galaxies, including the Andromeda Galaxy, M31, and NGC 3115. They consistently found that stars on the outer edges of these galaxies were orbiting at roughly the same speed as stars closer to the center, even far beyond where most of the visible light from the galaxy ended. For example, in the Andromeda Galaxy, stars 30,000 light-years from the center moved at speeds of about 200 kilometers per second, nearly identical to stars at 5,000 light-years. If the visible matter accounted for all the mass, the rotational velocities should have significantly decreased in the outer regions. This meant there had to be a significant amount of unseen mass extending far beyond the visible boundaries of the galaxies, providing the extra gravitational pull to keep those rapidly moving outer stars from being flung into intergalactic space. Without this invisible mass, the galaxies would simply tear themselves apart. Rubin famously remarked, "We were looking for something that wasn't there, and we found something that was." This wasn't an isolated anomaly, it was a pervasive pattern. Thousands of subsequent studies on hundreds of spiral and elliptical galaxies across the universe, using various observational techniques, confirmed these anomalous rotation curves. The pattern was consistent. Galaxies spin too fast for their visible matter alone. This suggested a vast spherical halo of invisible material enveloping each galaxy, extending far beyond the luminous disk, exerting the necessary gravitational influence. This evidence was more direct and pervasive than Zwicky's initial observations, and it couldn't be easily dismissed.
As observational technology advanced, another powerful tool emerged to detect the presence of dark matter: gravitational lensing. Predicted by Einstein's theory of general relativity, gravitational lensing occurs when a massive object, like a galaxy or a cluster of galaxies, bends the path of light rays from background objects. This bending effect distorts the images of the background galaxies, making them appear stretched, magnified, or even creating multiple images. The amount of distortion directly reveals the total mass of the foreground object, whether visible or invisible, because it's sensitive to all forms of mass, regardless of whether it emits light. Studies of massive galaxy clusters provided compelling support for dark matter. Astronomers observed powerful lensing effects in clusters like Abell 1689. By analyzing the distorted arcs and multiple images of background galaxies, they could create a precise map of the mass distribution within the cluster. These maps consistently showed that the observed lensing effect was far stronger than could be accounted for by the visible galaxies and hot X-ray emitting gas within the cluster. For instance, in Abell 1689, the mass inferred from lensing was found to be approximately 1,000 times the mass of its visible matter. This independently corroborated the idea that an immense amount of unseen mass pervades these cosmic structures, acting as the primary gravitational architect. More strikingly, the observed mass distribution from lensing often did not align perfectly with the distribution of visible light. Instead, the gravitational bumps were located in regions where there was no visible matter, but where dark matter was predicted to reside. This offered a powerful, independent confirmation of dark matter's presence, providing a direct measurement of its gravitational influence without relying on assumptions about stellar or gas dynamics.
The technique of weak gravitational lensing, which measures subtle distortions across vast swaths of sky, now allows cosmologists to map the distribution of dark matter on even larger scales, confirming its role in the formation of the cosmic web.
Beyond individual galaxies and clusters, dark matter plays a crucial role in the large-scale structure of the universe. Cosmological simulations, which model the evolution of the universe from the Big Bang to the present day, show that without
Dark matter, the universe would look drastically different. The early universe was incredibly smooth, with only tiny fluctuations in density. For these fluctuations to grow into the vast structures we see today, galaxies, clusters, and the enormous filaments and voids of the cosmic web, an additional gravitational pull was needed. Ordinary matter, composed of protons and neutrons, baryonic matter, interacts strongly with radiation. In the early universe, the intense radiation pressure would have prevented baryonic matter from clumping together efficiently enough to form the first stars and galaxies within the observed time frame. Dark matter, however, does not interact with light or radiation. It could have begun clumping together much earlier, forming gravitational seeds or potential wells into which ordinary matter could then fall, cool, and eventually form the first stars and galaxies. These simulations, run by supercomputers, consistently demonstrate that a universe dominated by cold dark matter, CDM, meaning particles that move slowly and were non-relativistic at the time of structure formation, reproduces the observed cosmic web with remarkable accuracy. The distribution of galaxies, the sizes and abundance of galaxy clusters, and the vast empty voids all align with predictions from CDM models. If dark matter didn't exist, or if it behaved differently, the universe would be a much smoother, less structured place, with galaxies forming much later and being far less abundant than what we observe. The evidence from the cosmic microwave background, CMB, also provides powerful support. The CMB is the afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old. Precise measurements from missions like NASA's WMAP and ESA's Planck satellite have revealed tiny temperature fluctuations in the CMB. The patterns and scales of these fluctuations are exquisitely sensitive to the composition of the early universe. Analysis of these CMB anisotropies confirms that ordinary matter accounts for only about 5% of the universe's total mass-energy density, while dark matter makes up about 27%. Without dark matter, the acoustic peaks in the CMB power spectrum would be entirely different, not matching the observed data. This confluence of evidence, from galactic scales to the very earliest moments of the universe, solidifies dark matter's role as the invisible architect of cosmic structure.
While galactic rotation curves and gravitational lensing provided strong circumstantial evidence, the bullet cluster, 1E0657-56, offered what many scientists consider the most direct and compelling proof yet for the existence of dark matter. The bullet cluster is not a single entity, but rather a pair of galaxy clusters that have undergone a massive, high-speed collision approximately 150 million years ago. It's essentially a cosmic car crash occurring on an immense scale. Astronomers studied this unique system using a combination of X-ray telescopes and optical telescopes with gravitational lensing analysis. When galaxy clusters collide, their components behave differently. The ordinary matter in clusters is primarily in the form of hot, diffuse gas that permeates the space between galaxies. This gas is so hot that it emits X-rays, making it visible to instruments like the Chandra X-ray Observatory. During a collision, this hot gas experiences significant drag and friction. It slows down, heats up, and forms a shock wave, often lagging behind the individual galaxies. Observations of the bullet cluster using Chandra revealed precisely this. The X-ray emitting gas was concentrated in the center, appearing flattened and lagging behind like the bullet in the wake of the collision. This is the ordinary baryonic matter of the cluster. However, when astronomers used gravitational lensing techniques to map the total mass distribution of the bullet cluster, they found something extraordinary. The majority of the mass, the gravitational lumps, did not coincide with the X-ray emitting gas. Instead, these mass concentrations were located precisely where the individual galaxies were.
The dark matter, inferred from the lensing effect, appeared to have passed straight through the collision relatively unimpeded, interacting only gravitationally, while the ordinary gas slammed into itself. This clear physical separation of ordinary matter, the X-ray gas, and the dominant gravitational mass, the dark matter, traced by the galaxies, provided irrefutable evidence. It showed that the missing mass was not simply ordinary gas, dust, or dim stars, as it behaved fundamentally differently during a high-speed collision. The dark matter had decoupled from the ordinary matter, a phenomenon that cannot be explained by any known form of baryonic matter. It strongly implies that dark matter is composed of exotic, non-baryonic particles that interact with each other and with ordinary matter only through gravity, and potentially the weak nuclear force. Hence its ability to ghost through the collision. The bullet cluster provided a smoking gun, a direct observation that dramatically distinguished dark matter from ordinary matter, solidifying its place as a separate and dominant component of the universe.
Given the overwhelming observational evidence, the scientific community largely accepts the existence of dark matter. The focus has now shifted to understanding its fundamental nature. What is it made of? The leading scientific theory is that dark matter consists of exotic, non-baryonic particles that do not interact with light or other electromagnetic radiation. This means they don't absorb, emit, or reflect photons, making them truly dark. Scientists at institutions like CERN, the European Organization for Nuclear Research, Fermilab in the United States, and various university research groups across the globe believe these particles are fundamentally different from protons, neutrons, and electrons, the particles that make up all the ordinary matter we know. The leading candidates for dark matter particles are weakly interacting massive particles, or WIMPs. This hypothesis emerged from particle physics theories that predict new particles existing just beyond the standard model. WIMPs would be massive, perhaps dozens to thousands of times the mass of a proton, and, crucially, would interact with ordinary matter only through gravity and the weak nuclear force. This explains why they are so difficult to detect directly and why they passed through the bullet cluster collision unaffected by electromagnetic forces. WIMPs are theoretically predicted in extensions to the standard model, such as supersymmetry, which posits that every known particle has a heavier superpartner. Another prominent candidate is the axion. Axions are much lighter than WIMPs, perhaps billions of times lighter than an electron, and are also predicted by solutions to a theoretical problem in quantum chromodynamics. They would interact even more weakly than WIMPs, and are actively being searched for in dedicated experiments. Other, more exotic candidates include sterile neutrinos, which are hypothetical neutrinos that do not interact via the weak force, unlike the active neutrinos we know. Some theories even consider primordial black holes as a form of dark matter, though current constraints suggest they would have to be either very small or very large, making them less favored as the primary component. The standard model of particle physics, which describes all known fundamental particles and forces, does not include any of these dark matter candidates. If dark matter is WIMP-like or axion-like, it necessitates new physics beyond the standard model, a profound expansion of our understanding of the fundamental building blocks of the universe. The sheer abundance of dark matter, 5 times more than ordinary matter, means that these hypothetical particles would dominate the cosmic inventory, profoundly impacting our understanding of matter itself. The quest to directly detect dark matter is one of the most significant and challenging endeavors in modern physics. Since dark matter interacts so weakly, scientists must employ extraordinary measures to even hope to catch a glimpse of it.
One primary approach is direct detection. These experiments are built deep underground, shielded from cosmic rays and other background radiation to minimize interference. They use extremely sensitive detectors designed to register the incredibly rare event of a dark matter particle, like a WIMP, colliding with an atomic nucleus in the detector material. Projects like Lux Zeppelin in South Dakota, Xenon NT in Italy, and Pandax in China are at the forefront, using supercool detectors filled with liquid xenon. The idea is that if a WIMP hits a xenon nucleus, It would cause a tiny flash of light and ionization, which the detectors would register.
So far, these experiments have yielded no definitive direct detection, continuously setting ever tighter limits on the possible mass and interaction strength of WIMPs, pushing the boundaries of what these particles could be.
Another approach is indirect detection. If dark matter particles are their own antiparticles or can self-annihilate, they might annihilate upon collision, producing detectable ordinary particles such as gamma rays, neutrinos, or antimatter, positrons.
Telescopes like the Fermi Gamma Ray Space Telescope are searching for characteristic gamma ray signatures from regions where dark matter is thought to be abundant, such as the galactic center or dwarf spheroidal galaxies, which are thought to be
Rich in dark matter. While some intriguing signals have been observed, none have been definitively attributed to dark matter annihilation. The Large Hadron Collider, LHC, at CERN also plays a role in the hunt for dark matter. Particle accelerators attempt to create dark matter particles in high-energy collisions, much like how the Higgs boson was discovered. If WIMPs are produced, they would escape the detectors unseen, leaving behind a missing energy signature. While the LHC has not yet directly produced dark matter, it continues to explore new physics that could shed light on its nature. Future missions and observations will continue to refine our understanding. Upcoming space telescopes like the Euclid Space Telescope, ESA, and the Roman Space Telescope, NASA, along with ground-based observatories like the Vera Rubin Observatory's Legacy Survey of Space and Time, LSST, will create unprecedentedly detailed maps of the universe's large-scale structure. By using more precise gravitational lensing measurements and galaxy distribution analysis, these observatories will map the distribution of dark matter with incredible accuracy, providing new insights into its properties and evolution. Recent breakthroughs in artificial intelligence and machine learning are also being deployed to sift through the vast datasets, potentially uncovering subtle patterns or signatures that betray dark matter's presence. These cutting-edge technologies and experimental programs are not just searching for a particle. They are exploring a new frontier of physics, a potential dark sector of particles and forces that could dramatically expand our standard model. The existence of dark matter presents some of the most profound implications for our understanding of reality itself. It forces us to acknowledge that the universe is far more mysterious and complex than our senses or our current instruments can directly perceive. First, the very composition of the universe is dominated by the unknown. The atoms that make up stars, planets, and ourselves, ordinary baryonic matter, constitute only about 5% of the total mass energy density of the universe. Dark matter makes up about 27%. The remaining 68% is dark energy, an even more enigmatic force driving the accelerated expansion of the universe. This means that 95% of the cosmos is made of components we cannot directly see or fully understand. Our familiar universe is merely a thin, luminous veneer over a vast, invisible cosmic ocean. The existence of dark matter suggests that our observable universe, the one composed of atoms, stars, and planets, is merely a subtle ripple on a far grander, invisible sea. This challenges our very perception of reality. Is dark matter a single type of particle, or is there a dark sector with its own complex array of particles and forces, analogous to our standard model? Could there be dark atoms, dark chemistry, or even dark life, interacting through dark forces, entirely separate from our own electromagnetic and strong nuclear forces? While highly speculative, these dark sector possibilities are not entirely ruled out by current evidence and are being explored theoretically. Unsolved mysteries and paradoxes abound. Why does dark matter exist in such abundance, outweighing ordinary matter by a factor of 5? What is its exact mass, spin, and other fundamental properties? Does it self-interact in ways we haven't yet detected, or is it truly a collisionless fluid? What role did it play in the very first moments after the Big Bang? And how did it influence the inflationary epoch and baryogenesis, the creation of ordinary matter? And if it is a particle, why has it so successfully eluded every attempt at direct detection, pushing WIMP candidates to ever smaller interaction cross-sections?
The implications extend to our understanding of gravity itself. While the consensus favors dark matter particles, some alternative theories propose that our understanding of gravity needs to be modified on galactic and cosmic scales, e.g., modified Newtonian dynamics, MOND. However, these theories face significant challenges explaining all observed phenomena, particularly the bullet cluster and the cosmic microwave background, which are elegantly explained by dark matter. The future of dark matter research holds multiple possible outcomes. We might one day directly detect a WIMP, confirming our current leading theory and opening a new chapter in particle physics. Or we might discover a completely new particle, or even an entirely new paradigm of physics, fundamentally altering our understanding of space, time, and matter. The journey to uncover dark matter's true nature is a journey into the fundamental laws that govern our universe.
Our journey through the evidence of dark matter has taken us from anomalous galactic rotation curves to powerful gravitational lenses, cosmic collisions, and the earliest moments of the universe. We have seen how observation after observation, from the small scales of galaxies to the large-scale structure of the cosmos, points to an invisible component that fundamentally shapes everything we see. Dark matter is no longer a fringe idea. It is an indispensable part of our standard cosmological model. We have learned that the universe is far more mysterious and complex than our senses or our current technologies can directly perceive.
The current scientific consensus is clear. Dark matter exists, it is non-baryonic, and it provides the gravitational glue that holds the universe together, acting as the invisible scaffolding upon which cosmic structure has formed. Yet, its true nature remains one of the most tantalizing and profound unsolved puzzles in science. The universe is vast. The mysteries are endless. The journey to unveil the invisible continues.